Imagine a universe where the very ingredients for life on Earth weren't always available. A groundbreaking new study reveals that the timing of planet formation within our galaxy is absolutely crucial, dictating a planet's composition and ultimately its potential to harbor life. But here's where it gets controversial. This research suggests that the building blocks for life didn't arrive all at once. So what does this mean for the search for extraterrestrial life? Scientists at UNLV, in collaboration with researchers from the Open University of Israel, have developed a first-of-its-kind model that explores how the timing of planet formation throughout the galaxy's history impacts a planet's density and makeup. Their research, published in the astrophysical journal Letters, highlights the critical link between the lives and deaths of stars and the birth of planets like our own. The full research paper is titled Effect of Galactic Chemical Evolution on Exoplanet Properties. The materials that go into making planets are formed inside of stars that have different lifetimes, explains Jason Steffen, an associate professor at UNLV and the lead author of the study. Think of it this way. Stars are cosmic foundries, forging the elements that eventually become planets. And just like different factories produce different goods, different stars create different elements over varying timescales. And this is the part most people miss. This difference in stellar life cycles has a profound impact on the planets that form around them. This research offers a compelling explanation for why older, rocky planets tend to be less dense than younger planets like Earth. Essentially, it boils down to stellar evolution and the cosmic timeline. All of the essential elements that constitute planets, oxygen, silicon, iron, nickel, and so on, are created within stars. Planets are constructed from the remnants of these stellar deaths. However, stars have vastly different lifespans, which significantly influences the composition of the planets they help create. High-mass stars, the rock stars of the cosmos, burn brightly and die young, typically within a mere 10 million years. When they explode as supernovae, they scatter lighter elements like oxygen, silicon, and magnesium into the surrounding space. These elements are often found in the outer layers or mantles of rocky planets. Now, consider low-mass stars. These are the cosmic marathon runners, living for billions of years. They gradually release heavier elements, such as iron and nickel, which are crucial for the formation of planetary cores. Planets that form in solar systems where both high-mass and low-mass stars have had sufficient time to contribute materials to the protoplanetary disk, the swirling cloud of gas and dust from which planets are born, will possess a greater diversity of elements. Planets that form primarily from the debris of high-mass stars will tend to have larger mantles and smaller cores. However, when low-mass stars have had ample time to contribute heavier elements, you end up with planets that have proportionally larger cores rich in iron and nickel. Interestingly, the research team had been developing software models for various specific projects over the past decade. It was only recently that they realized they possessed all the necessary components to create a fully integrated model of planet formation. As Steffen put it, it was like having the solution in hand, waiting for the right problem. The release of new observational data provided the final piece of the puzzle, allowing them to model the entire system with a relatively small addition of code. This sophisticated simulation tracks the complete life cycle of planet formation, from the birth of stars and the synthesis of elements to supernova explosions, collisions, planet formation, and the internal structure of planets. One implication of these findings is that the conditions for life don't start immediately, Steffen emphasizes. A lot of the elements needed for a habitable planet and for living organisms are made available at different times throughout galactic history. This has profound implications for where and when we might expect to find life beyond Earth. More information about this research can be found in the paper, Effect of Galactic Chemical Evolution on Exoplanet Properties by Jason H. Steffen et al., published in the Astrophysical Journal Letters. DOI 10.3847-2041-8213 AE0457. The original article, This content is based on is titled Planet Formation Depends on When It Happens. New model shows why, and was retrieved from https://phys.org News 2025 10 planetformation.html on October 17, 2025. So what do you think? Does this research change how we should search for habitable planets? Could it be that we've been looking in the wrong places or at the wrong times? And if the ingredients for life weren't always around, what does that say about the rarity or commonality of life in the universe? Share your thoughts in the comments below.